Okay, I guess we'll start soon. Just as a reminder, the canvas is due today, so hopefully, I haven't checked, but some of you probably have submitted. The final presentation is on Thursday, and the video pitch is due Friday. So this are the main things. And yeah, welcome to the last week of class. Let's see, a lot of you, only a few of you are here, which is fine. Hopefully everyone will make it on the last day. So today what I want to talk about is some interesting new things that are in the horizon. So that this is kind of the last lecture. So I wanted to talk about some exciting stuff that's happening. And then we'll kind of try to summarize some of the things in the class. But that's my goal today. It will be a little bit, I guess, maybe shorter than usual, so you have a bit more time to work on your projects. Okay, but before I start, are there any questions, either on chat or? Okay, I don't see anything, so I guess let's get started. So today's lecture is on broadband diffractive optics, so spectrum splitting and photovoltaics. So the idea here is, this is just an example of some interesting thing you can do with optics in order to improve the efficiency of solar cells. And I'm treating this as an example of an innovation that we worked on in my lab. Now, first of all, let's lay the groundwork of why we're trying to do this. There we go. So the motivation is that, of course, in order to have widespread usage of PV, we need to reduce the cost. And we've been talking about this quite incessantly, I guess, throughout the semester. So we want to understand what is it that we can do. Of course, there's been a huge effort on reducing the materials cost for over many decades. So today, the cost of a solar panel is, about 10 times less than it was maybe a little more than a decade ago. So that's a pretty dramatic reduction. But the vast majority of that has come with just reducing the cost of the materials themselves, a little bit on the cost of the balance of systems, installation, and things like that. But I want to talk about something slightly different here, which is, if you look at how the PV costs break down, approximately half is the module, which you can see here. Half of it is in the installation cost. In the what's called the balance of systems and installation. So BOS, of course, stands for balance of systems, as some of you know. Oops. And make sure it's connected. And that refers to things like transportation, installation, regulatory costs, application for licensing and things like that kind of stuff. So about half of it is that, and the small sliver is power electronics. This has been pretty consistent for a long time. So So what can we do to really reduce these costs? Now, the module cost, there's not a lot you can do other than, getting cheaper materials, get a cheaper manufacturing. There's all kinds of different things like that, right? So this has been the big emphasis for a very long time. Now, what I want to talk about is, could we address all of this together? And this was something that has been recognized for a while, and that has to do with efficiency. So how important is module efficiency? And this was studied several years ago by some folks in this. I'm just picking one example from George Washington University, where they plotted the dollars per watt, so the electricity price, cost, let's say, on the vertical axis versus system efficiency on the horizontal axis. And of course, as you expect, as efficiency increases, that means with the same installation, you're producing more power. That means your balance of systems costs go down. Your power electronics per watt goes down, cost per watt, and your panel cost per watt goes down. So all the different aspects can be reduced by increasing the efficiency. That's basically what this is saying. But if you look at this a little more closely, what does it mean? So let's take the example of the residential, which is this curve here. You can see, for a 5% efficiency, you get something like $3.25. But if you go to a 25% efficiency, which is kind of the state of the art, I would say in that order, 20 to 25%, costs about $1. So that reduction going from 5% to 25% in terms of efficiency can make a pretty dramatic difference, like 300% increase, right? Something like that. So this is what we're trying to do. And of course, different systems, here they're looking at residential, commercial tilted, commercial flat, and so on and so forth, and tracking and things like that. Of course, with concentration, you can get higher efficiencies. So some of these, of course, scale faster than others. But a very interesting conclusion that came in this study is what I picked out in the bottom. If you're taking a very simple example of a 5% efficient module, very low efficiency, and let's say you give it away for free, okay, it doesn't cost anything, that is equivalent, it has the same system electricity price of about $3.50 per watt, DC watt, as a 15% efficient module that you can charge, I forget the exact number, but something about $1.50 per watt. In other words, a higher efficient system, of course, you can charge more for it, right? Because you're producing more electricity. So it's kind of common sense, but it's an interesting thing to kind of think about, that if you have a very low efficient system, it may not even make sense if the panel cost itself was completely free, because there's all the other costs, right? Balance of systems and power electronics and things like that. So the efficiency turns out to be a pretty critical factor. And this is another way to look at it. Here, we're plotting the levelized cost of electricity on the horizontal axis, which is, by the way, if you open up your utility bill, this is what you'll see, cents per kilowatt hour or whatever, whether it's coal or natural gas or solar, the units are all the same. Then on the vertical axis, we have the module cost. So this is only 50% of the total installation cost, right? So what's plotted here is that different module efficiencies give different slopes to this curve, and these are logarithmic in the vertical axis. So a low efficiency curve has a low slope. In other words, as your module cost increases, levelized cost of electricity increases faster. Whereas with a high efficiency, it sharpens up, which means that for the same levelized cost, let's say that's a 6 cents per kilowatt hour, that's our goal. If you have a low efficiency module, the module cost has to be quite low. In this case, let's see, this is, I don't know, $7 per meter squared. This is an aerial cost. Whereas if you have a very high efficiency module, you can charge up to, I don't know, $125 per meter squared. So a 2x increase in efficiency or 2.5x increase in efficiency leads to more than 10x increase in your module cost that you can charge. So it makes a lot of business commercial sense as well to increase efficiency. Now let's think more fundamentally about, where does the light go? And we talked about this before, so I want to kind of come back to this point, is that if you have a single bandgap semiconductor, it does not match the solar spectrum. So we know the solar spectrum spans a huge range of wavelengths going from the UV down here, all the way, this is visible, all the way to the infrared. Right? It's a pretty huge range, something like 300 nanometers all the way to 1,000 nanometers. Now, this is, of course, the relative output from the sun. Now, if I only have one solar cell, one bandgap, my bandgap of silicon is about here somewhere. Anything below this has higher energy in the bandgap and can be absorbed. Anything above this does not have enough energy and will not be absorbed. But all the photons here are not equally absorbed. This is the key point. Okay, and we saw this before. So let's look at this in a little more detail. Where does the energy go? So there are several things that can happen, right? Let's start at the top. So our single bandgap semiconductor can be modeled with a conduction band here, a valence band down here. The valence band is filled with electrons. Conduction band has lots of unfilled energy states we call holes, right? Now, and they're separated by a bandgap, Eg. Now, a photon comes in, its energy is h nu. What happens? There are many things that can happen. If the energy of the photon is equal to the bandgap, then there's a very high probability that the photon will be absorbed and the electron will jump up into the conduction band. And this is good. This is what we want. This electron now can move to the anode. This hole can move to the cathode and run the current and do work. Okay, that's the ideal situation. We call it radiative. This is absorption. Right? This is the photoelectric. Now, of course, many other things can happen. This is not the only thing. If the energy of the photon is less than the bandgap, the photon does not have enough energy to kick the electron out of the valence band. It won't be absorbed. It will pass straight through, as shown here. And this is what happens in the case of glass, right? Glass is transparent to visible light because nothing is absorbed, just passes through. Not enough energy to the bandgap of glass, silicon dioxide is too high. Silicon dioxide, by the way, is amorphous, so it's not an exact analogy, but imagine that. Now, you can have so that's not good. That means if the energy, if the bandgap is too high, then a lot of the photons may not be absorbed. If the bandgap is too low, then you have other problems, which is an example is the thermalization loss. So in this case, the photon energy is much higher than the bandgap. What happens? The energy of the photon is so high that it kicks out an electron from way down below the valence band all the way to way above the conduction band. Now, this might sound like a good idea, but it has a fundamental problem dictated by quantum mechanics. These states up here, this is a band, right? There's a continuous set of states. That means those electrons, although it might have a higher energy, cannot survive there very long. It doesn't have a very long lifetime. It very, very quickly relaxes down to this band edge. Okay? And this happens really, really fast in picoseconds or femtoseconds, actually. Now, and the same thing happens on this side with the holes. That means this energy is essentially lost as heat into the crystal lattice. It's very similar to the Stokes shift we talked about before. And then of course, then the electron can go on and do work and so on. So that's good, except that what happened to this difference, h nu minus Eg, is lost. So you're still not absorbing as well as you would like to. Now, you can also have a situation of, in this ideal case, instead of going out and doing work as we would like to the terminals of a battery, charging a battery, whatever, you can also do what's called radiative recombination. The electron can simply come down and emit another photon like fluorescence or phosphorescence or something like that. Then you lose that energy also. So that's a bad thing as well. Now, there are many other things that can happen, but this is a simplistic way to think about it. Just to summarize, for us, from a simplistic perspective, there are only three things that can happen. One, the photon is not absorbed. Nothing happens, passes through. Two, the photon is absorbed, but is absorbed with much higher energy. The energy of the photon is so high that you lost that extra energy as heat in the crystal. And three, you can have a non-radiative recombination. Radiative recombination, which means that the photons are absorbed, but they immediately recombine and another photon is escaped. So in other words, no work is done. So those are three primary loss mechanisms. So if I go back to the spectrum, what that really means is that if I only have one band gap here, of course, this part is useless because it's not absorbed, as we just talked about, not enough energy to kick the electron from the valence band to the conduction band. out here, which is far from the band gap, it has too much energy. That extra energy is simply not collected efficiently. It's just lost this heat in the crystal. So the only part that's collected is something close to the band gap, collected efficiently. So this is a fundamental problem that we think about. Now, we can also visualize this slightly differently. There's an important paper written by Harry Atwater and others 10 years ago now, which looks at, okay, where does the actual energy go? How do we account for this? It's simply an accounting thing. So a single junction solar cell, this is efficiency. You start at 100%, of course. You have energy loss in the Carnot cycle. This is the thermodynamic limit dictated by the second law of thermodynamics, as we have talked about before. There's something called an entropy loss. We're going to skip, we didn't talk about it, so I'm going to skip these two things. Not terribly important. There are small numbers there. This is the part we just talked about. This is a big chunk. You can see it's a huge part of the loss, right? This is the thermalization, that extra energy, and the non-absorption loss. Now, you also have other things like entropy loss due to angle restriction. I'm going to skip those, not terribly important. Reduce QE because incomplete light trapping. We talked briefly about that, small effect. And we end up with the conventional single junction solar cell. This is the best one can hope to do with a single photovoltaic, single semiconductor bandgap. About 30%, something like 31%. This is a theoretical limit. Now, of course, you can go a little bit higher with concentration and all that, but not a lot. Now, we have all, and the vast, this is the part that I want to talk about, because this is a big loss mechanism. Okay. Now, of course, you already know a solution to this, which is the multi-junction solar cell. Right? This is, for example, the solar cell that's used in space, in the Mars rover, and so on and so forth. The way it works is described on the right-hand side, where you have three cells. So you have a top cell connected to a middle cell, connected to a bottom cell. High energy photons are absorbed in the top cell, slightly lower energy photons absorbed. Sorry, lowest energy photons absorbed. Yes, I'm getting confused here. The highest energy photons absorbed in the top cell, the middle energy photons absorbed in the middle cell, the lowest energy photons absorbed in the bottommost cell. And that makes sense because the top cell has a very high band gap. So all the photons on the right of it will not be absorbed. They'll just pass through, right? It's like glass and so on and so forth. So by separating out the portions of the sunlight, you can absorb them more efficiently. That's the idea. And of course, you've seen this before. And you've seen cells which look like on the left-hand side. In this example, the top cell, indium gallium phosphide, has a high band gap. Indium gallium arsenide, the middle cell, has slightly lower band gap. And germanium, of course, is the lowest band gap at the bottom. Now, what's the problem with this? And you guys already kind of know this, but let's reiterate the issues so we can understand this. First of all, as you can see, the device itself is very complicated. Like, you've got lots of layers here. You can see germanium, multiple layers, BSF, base, hetero layer, buffer layer, all this kind of stuff. And each of them take a lot of effort to grow because these are not simply grown like a crystal growth. You have to grow them with what's called an epitaxial growth, which means you have to put down one atomic layer after another. Let's look at what that means shortly. And the reason to do this has to do with lattice matching. So there are different materials. There was germanium, then there was indium gallium arsenide, and then gallium arsenide. If you look at the lattice structure of germanium, that differs from the lattice structure of indium gallium arsenide. I'm just giving an example. The lattice structure here does not match the lattice structure. So what that means is that when you try to grow them, you need to grow them very, very carefully, and you still end up with defects as shown here. There's a missing atom here. Right? There's a missing lattice atom here. And that's very problematic because what that thing is, that T-like structure, inverted T-like structure there, is a dangling bond. And the dangling bond means there are electronic orbitals or states within the band gap. There are defect states within the band gap into which the electrons can get trapped. And they will not reach the battery and do work. And if there are too many of those, you will get lots of those electrons trapped in there. And then your efficiency of the solar cell degrades. So this is why it's very, very critical in order to get a very high efficiency solar cell. You need to try to avoid things like that. You need to make this with very, very high purity, very, very carefully. This is called lattice matching. Turns out to be very hard. The second problem is something electrical engineers can appreciate is current matching. So I told you these cells were basically on top of each other, right? There's one cell here, another cell here, another cell here, and so on. I can also draw these as diodes, right? These are reverse bias diodes, like that. Right? And you can see these diodes are now connected in series. And now connection in series means what? It means that the current all have to be the same. Voltages can be different, but the current essentially has to be the same. And the current now is limited by your poorest performing diode or poorest performing solar cell. So an example is shown in the bottom here, that I have a top cell, which is producing some current of 1 arbitrary units. I have a middle cell that's producing roughly the same, which is good. So they match. But I have a bottom cell, which is producing a lot more. But if I connect all of them in series, what happens? This excess current can no longer flow through these two because they're in series. So this automatically comes down to the bottom, the minimum level. So in other words, when you connect these cells in series, the highest current you can hope to get is limited by the worst performing cell in that series. That's terrible, right? Now, by the way, this is also, you can understand this from the spectrum as well. If I look at the bottom cell, germanium, it is collecting a lot more photons, right? It has a huge band here that's collecting light from. Remember the flux, there's lots more photons, the number of photons there. Whereas the middle cell is only collecting that much and the top cell is collecting that much. So these are roughly the same, but this is much higher, right? This is the number of photons. And current is, of course, determined by the number of electrons. Has nothing to do, well, has something, but not much to do with energy. So here, what I'm saying is that when you connect them in series, you're automatically putting your best performing cell at a disadvantage. It's going to produce less current. Now, of course, less current means that the total power will be lower as well because the power is simply current multiplied by voltage. So current matching is an issue. Of course, you can think of other ways to do this, right? I can make it so that they're completely independent and not have this connection at all. That is possible, but it's really hard to do. People have tried to do this. It's really hard to do because then you have to make separate devices. When you have separate devices, there's too much reflection losses from these interfaces that you see here. So you end up with too much loss there. But there are solutions that people have looked at and still looking at. And of course, at the end of the day, this turns out to be very expensive and really only makes sense if you're trying to send things to space where cost is really not an issue. You can really deploy this on Earth. Although there are people, there's a company, I think we talked about it, Alta Device.